Welcome back, Spidey fans. Today I got an interesting video again. It's a follow-up video from the last one I posted, which was the 3D Schrödinger equation. We split up the Schrödinger equation into three different equations. The angular equation is made up of two, the azimuthal portion and the polar portion. So this is the angular equation, and then we have the radial equation. Today we'll be looking at just the angular equation. There is a way to solve these complex differential equations. We're not going to look at it today. We're just going to look at the solutions of these differential equations while solving a problem, a very interesting problem. You can see over here I have marked this little star in green. Griffith says these problems are very important, so we got a problem that we gotta do. We cannot skip this one. Problem 4.4. What this problem says is use equation 4.27, 4.28, and 4.32 to construct capital Y subscript and superscript 0 and capital Y subscript 2 superscript 1. Check that they are normalized and orthonormal. What does this mean? These Y's are functions that are the solutions to the angular equation. They're the spherical harmonics. I have written them over here. This is equation 4.32 from the amazing man, Mr. Griffiths. As you can see, the function over here depends on the angular variables theta and phi, which we created the differential equation for in the 3D Schrödinger equation in the previous video. But you can see this function also depends on two other things, these quantum numbers, the quantum number m and l. These things have physical properties. We don't know what they are yet. We're just going to work with the function. And you can see the function looks quite scary. But it is pretty cool if you break it up into three portions. There's this big portion here. It is the normalization factor. It only depends on numbers and these L and M things and some factorials. You know, we got a 4 pi right here. We got L plus M factorial. So a bunch of just numbers. Here is our first function. This is a complex exponential e to the I m phi. This comes from the phi differential equation. And here we have another function. This is a function within a function. And what's crazy is this function is right over here. It is the associated Legendre function. You can see it right here. And what's even crazier is inside this function is yet another function which we have over here, which is given by the Rodriguez formula. And this is the Legendre polynomials. So this is a crazy thing. The spherical harmonics are created by nested functions, and they are the solutions to the three-dimensional Schrödinger equation, specifically the angular part of that. And yeah, what more can I say about this? I mean, we're going to plot them in a future video. We're going to look at what they look like. But today, what we're going to do is use these three functions right here to construct the 0, 0 and the 1, 2 spherical harmonics. After that, keep in mind what we're doing here. This is quantum mechanics. These things represent wave functions, probability densities of some system, specifically in 3 dimensions, some quantum system. And what we learned in chapter 1, 2, and 3 is that these wave functions can be normalized and they can be orthogonal to each other. Okay, so what does that mean? I think this part, check that they are normalized and orthogonal, we're going to do second. First, I'm going to construct these to show you how easy it is. It is pretty easy. I mean, we have the Lego pieces right here in front of us, so that's what we're going to do. And then in the second part, we're going to normalize and check their orthogonality, which might be quite long. So grab some snacks, grab some water. Let's check what we do here. So first things first, construct. It's cool how they use this word. Y, I'm going to use this capital 0, 0. How do we do this? Well, we have Y, and then the top letter here is M, L. This thing depends on theta and phi. So what we have here is, well, I'm just going to write M equals 0 and L equals 0, because now we can substitute things inside this big square root. 2 times 0 is just 0, and 0 plus 1 is just 1. All right, I'm looking up here. 2 times 0, we have L equals 0. We just plug a 0 in here. 2 times 0 equals 0 plus 1. This gives us 1. L minus M. Here we have 0 minus 0. 0 minus 0. 0 factorial. I think 0 factorial is actually defined as 1, because if you check in the denominator, we have L plus M. In our case, it's going to be 0 plus 0 factorial. And if 0 factorial equals 0, we have a 0 in the denominator, which is not okay. So just from that kind of problem, I can remember that 0 factorial is defined as 1. What does that mean? That's another video. Check a math channel if you guys are interested. But if it equals 0, then we are screwed. So I know it has to equal 1. I hope that's okay with you guys. Here we have a 4 pi, right? Then here we have, 0 factorial, which is 1. So this is the end of our square root. 1 over 4 pi. Nice. Now what do we have here? E to the im phi. This is e to the 0, and this just equals 1. So we could erase that as well. Actually, I'm going to keep that, do a little line here, and just say equals 1. So it looks a little bit more intelligible. All right. Now we have to use these other functions, which I'm going to do just below in... Actually, I'm going to do it right here so you guys can see what's happening. We have P00, 0, and inside here we have cosine theta. So what does this function equal? Well, I'm going to take a look right here. Boom. Fairly easy. We're just going to plug in minus 1 to the 0th power just equals 1 times 1 minus x. But in this case, x is cosine theta. How do we work with this? I could do cosine theta squared because that's the x. But you know what? I'm just going to keep it as x because there's a derivative with respect to x later on. And if we start putting cosine thetas in here, it's going to get very confusing. Anyway, here we have an m to the 1/2. So we have 0. So this whole thing goes to 1 anyway. Or not 0, 1. Then we have a derivative to the mth power, and m is equal to 0. So we don't have a derivative at all. Derivative. See, I have a dx here. If I change everything to cosine, I'm going to have to put d cosine theta there, which just looks scary. So this whole thing also goes to 1. You apply this operator 0 times. Then we have the PL, which I'm going to write in pink. Take this whole thing, slide it over here. So right here we have this PL, which is 1 over 2 to the L, so 2 to the 0 times 0 factorial. I think all of this stuff just goes to 1, 1, and 1. Not too bad. Then we have another derivative, which I'm again keep in pink. D dx, and this is again 0. So this whole thing also just goes to 1. And then we have x squared minus 1 to the L, which is 0. So this whole thing again just goes to 1. Okay, so see what I did here? This entire pink part is the PL equals 0 of x. And this entire part right here is this Legendre, associated Legendre function. So what does this whole thing equal? Well, we have a 1 here. We have 1, 1, 1 over 1, 1, 1, 1. So this whole thing, 0, 0, just equals 1. So we're going to go back here and just do times 1. So this part here, actually maybe I'll just use a laser pointer. This part here was literally just this part here, right? This 1 was just this function here, and this entire thing here was just this one. So what does this whole thing equal? Let's check. It equals square root 4 pi in the denominator, 1. That's it. This equals y 0, 0. The L equals 0 and M equals 0 spherical harmonic. Not too bad. Now let's do the same thing for, what is the other one they give us? Probably going to be a hard one. 1 and 2. 1 and 2. Okay, this is going to be a harder one. Actually, let me just bring this guy down further here so I can see what's going on. Whoops. Put this guy here. Okay. Let me separate this because it's probably going to get hectic. Alrighty, start off with the square root. I'm gonna also write m equals 1, L equals 2. Is that true? 1 and 2. Okay. Let's start working here. So we have 2 times L, which is 1, plus 1. Nice. Now here we have a 4 pi. And then here we have a L minus M. L is 2, M is 1, and this is factorial. And then here we have L plus M. L is 2 plus 1, which is M, factorial, and that is our square root. We can cut that off right here. Boom. Now we have an e to the I m. M is 1 phi, so 1 is just left there. Now we have the p m equals 1, L equals 2 of cosine theta. So this thing, maybe I'll do in this salmon color here. Boom. What does this equal? Equals question mark? Or let's just say it equals this star. So I'm going to do star over here equals, and then bring into play this guy. Actually, probably I should keep this here, keep things clean. Boom. Duplicate this guy and bring it down here so I could use it. Nice. Alright, so I'm going to continue with the salmon color. We have m equals 1 and L equals 2. Here we have a negative 1 to the m, which is 1. Right, so that's going to give us a negative 1. Here I have 1 minus. I'm going to keep the x, and then later we're going to bring in the theta, or the cosine theta. You guys are going to see what I mean. Here we have an m, 1 half. Oof, this is looking crazy, guys. Here I have a derivative. I'm going to keep the derivative like this in the brackets. And the derivative is to the power of the m, so m is 1. We take a first order derivative, that's amazing. And then here we have a p, L equals 2 of x. But we have to put a cosine in there as well. So I'm going to check this out. Right? We have this function, duplicate this guy. Bring it down here. You gotta just look at the functions if it is confusing. Okay, what is PL equals 2? This is 1 over 2 to the L, which is 2 to the 2, and then we have times 2 factorial. Not bad. Then we have a derivative with respect to x, d dx, to the power of L, which is 2. Then we have x squared minus 1, which is L. Oh, L here is a 2. Okay, you know what, guys? What I'm going to do is actually change this whole thing to a different color. Let's do this blue here. So what's happening here? Check it out. What we have to find is this thing. Once we find that thing, we find this whole function, which is going to look crazy, I'll be real with you. But keep in mind, in here we're not putting x, we are actually putting cosine theta. But inside this function, we have everything in terms of x over here. You see this? So eventually, we're going to have to change that x for this cosine theta, but I want to do that all the way at the end because I don't want to take derivatives of cosine theta. It's going to be the same thing, you just got to do an extra u sub, but it's going to get confusing. But we have to do it in steps. So first, what I think I'm going to do is calculate this, which is given to us over here in terms of x. Plug that back in here, and then we're going to have a whole big function that is this. We're going to have to take another derivative here. And then once everything is simplified here, we're going to plug in the cosine theta. Is that okay with you guys? Alright, I hope that's good. So what we're going to do is calculate this guy here. 1 over 2 to the power of 2 is 4, and 2 factorial is 2 times 1, which is 2, and 2 times 4 is 8. Let me draw this 8 a little better. I draw my 8s like this. Boom. Now I have a derivative of this. Oh, man. Okay, you know what? I'm going to do a u sub here, because if we do u sub here, u is equal to x squared minus 1. And then du is going to equal to 2x dx. Why are we doing a u sub? Derivative. No, we don't gotta do u sub. U sub is for integrals. Look at me geeking out. All we can do is take a derivative. We take a derivative of this whole thing as if it's u, right? Bring this down, boom, and then derivative of this chain rule. Alright? That looks good, but we gotta do that twice, bro. Okay. Here I'm gonna write d dx, right? Inside that, I'm gonna take the derivative of this whole thing. So 2 times minus 1 like this, and then derivative of that is 2 times x. Okay, now derivative of that is 1 over 8. Derivative of this. How do we even do this, brother? How do we even do this? I guess we have to FOIL everything over, huh? Let me simplify this up here. So 2 times 2 is 4, and x squared times x is x cubed, minus 1 times 2 times 2, 4 times x. Okay, that looks okay to me. Now we get a derivative of that thing in green, which looks okay to me. But I'm going to put brackets like this. So the 3 comes down, with my bracket geeking. 3 times 4 is 12. Then we have x to the second power minus 4. Not bad, actually, not bad. Okay, what I did, guys, here, and I'm going to maybe erase some stuff or maybe copy some stuff somewhere. What I did was I have this function here, which is this function in blue. First thing I did was take the first derivative, right? This derivative has to be applied twice. So I just take the derivative, right? There's one derivative left here, and then I applied the derivative inside here to this thing, right? This 2 comes down, 2 times u, 2 times u, and then the derivative of u is x squared minus 1. The derivative of that is just 2x. Okay, so then I simplify this whole thing. It looks like this. What I did was just FOIL over this 2, FOIL over this 2, that becomes a 4. FOIL over this x, or distribute, I don't know, I'm using the word FOIL. So 4, this x squared becomes x cubed because of this x. FOIL over this 2, and this x. 2 times 2 equals 4, and x times 1 equals x. Now I take this derivative again, apply to this thing. That derivative is just 3 comes down, multiplies by the 4, boom, you get 12. This 3 minus 1 equals 2, and this 4 gets peeled off the x, no x. So this is our whole thing for this. Okay. You know what, I kind of want to keep this because I know that we might mess something up, but I'm going to take it like this, boom. See what I'm taking? I'm taking everything here, copy, paste this bad boy right here. And then here we can move this over here, and we can actually change the color to this salmon that I had before, and we can proceed. So now we're still looking for the star, which is over here. Once we calculate the star, we can put that in the original function, and we're going to find this. I hope you guys are seeing where normalization and orthogonality checks are going to go, because it's going to be crazy. Okay, now we have another derivative. This derivative, thankfully, is only applied one time to this whole thing. So let's do it, but let's simplify the whole thing. So 1 to the power of negative 1 to the power of 1 is just negative 1. Put that in brackets. Here we have 1 minus x squared to the power of 1/2. Then here we take the derivative. So 1 over 8, the derivative comes out. Then we have 24 times x, and that's it. Huh? Not bad, actually, not bad. Okay. Now we can take this whole thing. You guys see? Boom. Copy. Paste. So we have a minus sign. I'm going to pull the minus sign all the way out here in the front. Then we have a square root 1 minus x squared. And then here we have 24x over 8. But we did something gravely incorrect. Cosine, not incorrect, but we just missed something. This cosine is placed everywhere there is an x. Here, 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 here. But if we solved everything in terms of x, then here we could just replace everything that is x cosine. right? So there's an x right here. And this now becomes cosine squared theta, right? And here there's an x. So we have 24 cosine theta. Because remember, at the end of the day, this thing depends on theta and phi. So here is the phi and here is the theta. This gives us the spherical harmonic, which is L equals 2, M equals 1. Much more complicated looking than the first one here, which is just a straight constant. Think about what these spherical harmonics are. They're functions where theta is like this and phi is like this changes. So if we're saying this one is just a constant, then theta and phi can change everywhere and their value is always going to be the same. So what this one looks like, this one right here, is just a ball. But this one is much more complicated. Alright guys, so I went to Wikipedia and checked the table of spherical harmonics. Here is what I got for the 0, 1. 1 over 2 here. We have a square root 1 over 4. 1 over square root of 4, right? Because square root of 1 is just 1. Square root of 4 is 2. So this 2 comes out and square root of pi stays there. So we got this one right. Boom, check. But this one looks a little wonky. Right? First thing I noticed is here I did not simplify this. I could have done that. I'm going to do that right now. Here we have I phi. Here is that. Here we have a cosine theta and then some more numbers. Here we have a cosine theta, but then here, square root of 1 minus cosine squared theta. What I think is happening here is, if you remember, sine squared x plus cosine squared x is equal to 1. If you move the cosine here, is going to have a minus sine cosine squared x, right? It gets disputed here. And if we take square root of both sides, right, this is what we have here, and square root of this just remove this. So that's where this sign comes from, and that's where this sign comes from over here. So this looks good. And there's a minus sign here, and there's a minus sign here. So this, all this stuff here, and this 24 and 8 have to work out to be this, which I don't think should be a problem. So I'm going to just put this over here to the side in case I mess anything up. I don't want to go through all the orthogonality stuff and realize like I had something incorrect. So it's good to check your work. But if you are doing this on a test, you may not be able to simplify as fast. So enjoy what I'm doing here. You may not have to do the same thing. All right, so we have a 24 over 8. Let me do some mental math. 24 over 8, if you divide this by 2, you get a 12. If you divide this by 2, you get a 4. And then divide this by 2, you get a 6 and a 2. And then a 3 and a 1. So you just get a 3. Okay, gang. That was maybe showing a little bit of my goofiness with elementary math. I don't know how many times 8 goes into 24. But no stress. Alright, here we have 2 times 1 plus 1. 2 times 1 is 2 plus 1 is 3. Then here we have a 4 pi left over. Then here we have 2 minus 1, 1. 1 factorial is just 1. 2 plus 1, 3. 3 factorial. 3 times 2 is 6. Times 1 is 6. Then here we have an e to the I phi. Sine theta, cosine theta. Okay, can we simplify this more? Let's see here. So what I have here is minus 3 times, okay, square root of 4 is 2 again, so we can pull a 2 out like that. And then here we have a pi left, and we have a 3 over 6. Divide both by 3, we get a 1 here, and then we get a 2. I think that looks okay actually. But where's this 15 coming from? Okay, so what we have so far is minus 3 over 2 square root of 1 over 2 pi. So what we're looking at is everything in here is good except, well, we have this minus 1/2 here, but we have an extra 3. And then boom, here 15, and the 2 pi is here. How do we get a 15? Square root of 15. Wait, could I not have pulled something out? Oh wait, maybe I forgot a factorial. Let me check. 2L plus 1. Boy, where's this 15 coming from? Are you guys sure it's 15? Maybe I pulled something out that is not allowed to be pulled out. Oh wait. No. Okay, we got a problem. We made some mistake here. It's literally this 15, huh? Square root of 15. Where's this coming from? Okay, what we have here, to me, looks correct. Let's copy this and bring it down here. How long is the video? 30 minutes. Okay, not bad, but we still haven't done any orthogonality checks. And that's going to be the heavy hitter. Okay, so we have a 2L. Ah, here it is. Haha. 2L, and I thought that L was a 1, but it's not. L is 2 here. Silly, silly. 2 times 2? 2 times 2 is 4 plus 1 is 5. Aha. Aha. But I think that still fucks us, no? No? Okay. Erase all this because this was wrong. And that 3 stays there. Okay, so what we got is 5. This is looking better. Over... Oh, that 3 has to get brought in, huh? Square root of 3 gets brought in. Multiplies the 5. Huh. So there is a 3 here, and if this 3 gets multiplied by the 5, we do get the 15, but the 3 is not inside the square root. How do we bring the 3 in the square root? It has to be a 9. It has to be a 9. But then the 6 gets cancelled somehow. Okay, here's what we're going to do. This 3 gets removed and placed here in a 9, because square root of 9 is 3. This pi on the bottom stays, and the 4 in front of it comes out in the front to match. Then here we have 2 minus 1, 1. 1 factorial is 1. We're going to leave that as is. And then 2 plus 1 is 3. Factorial. 3 times 2 is 6. I think this makes sense. Ooh, this makes sense. Okay, here's what we have. 5 times 9 over pi times 6. So, 5 times 3 times 3. 3 times 3 is 9. And then here we have a 2 pi times 3, because 2 times 3 is 6. One of these cancels with one of these. This combines to be a 15, and we have what we're looking for. Damn. Okay, maybe that was long, but this is math, guys. You gotta grind out the math. Alright, so what we have is 1/2 square root 15 2 pi. If you don't have Wikipedia or a table of these guys there next to you on the test, don't worry about it. I'm just doing this for some practice. You know, at the end of the day, it doesn't really matter. You don't have to compute this, you know, with your head. You can use a computer. Main thing is, how do you work with this? How do you work with these nested functions, and how do you compute them properly? So check out that procedure, but don't worry about the simplification at the end. I don't think it's a big deal. Alright, now what do? Well, we have two functions. These are the wave functions, the spherical harmonics. And remember, if we have a function, you know, psi, let me write this. If we have a function psi, normalization means this. Or if we're in one dimension, these are functions of x. That's what it means. And orthonormality means psi, and let me do phi like this. So psi x phi x dx. Normalization means the inner product of these two guys is going to equal 1. So the particle has to be found somewhere. This represents a probability distribution, and integrating over all space gives you a 100% chance of finding the particle somewhere. Orthonormality is basically, are these functions linearly independent? Are they perpendicular to each other? Perpendicular, so to speak. We're not really working with exact right angles here. Orthogonal is probably the right way of saying it. But we're going to check this. So how do we check this? Let's check if this one and itself equals 1. Is this true? So we're going to integrate. But what do we integrate over? We're integrating over all of space, and in this case we have two integrals, right? Because we have two variables. We have theta and we have phi. And I think how I remember this is, which one is theta and which one is phi? Oh man, this is gonna trip me out. Okay, phi is the azimuthal angle. So phi, I think, goes from 0 to 2 pi, and theta goes from negative pi to pi. Is this true? This might mess us up. This might mess us up, and this is the important thing, guys. We're integrating over all of space. When we worked with x, x was the real number line, so we have to integrate from negative infinity all the way to positive infinity. Now we're working with angular components. So one of them goes from the top, sweeps all the way to the bottom. This is the polar one, I think. And this one, I think, is theta. So the inner integral is this one. This one goes from pi all the way to negative pi. Let me think here though. And the other one sweeps from x all the way 360 degrees or 2 pi radians back to x. And this one I think is the polar one, which is phi. We're going to see this with the second one, but this one here is going to be pretty simple. So we just have square root 1 over 4 pi times square root 1 over 4 pi. There's no complex conjugates here because the first one is just a real constant, so the complex conjugate of that is itself. We're chilling. And doing this integral is actually fairly easy. What we're going to get is this. We can pull it out of the integral and the square root gets removed. Now we have 0, 2 pi here. And these integrals we could actually do by themselves, I think. So this one combines with the d phi, and this one negative pi 2 pi goes with the d theta. Okay, so d theta, let's check what's happening here. This is 4 pi 1. Here we get a phi 0 to 2 pi. Right, pretty simple integral. And this one is negative pi 2 pi. Okay, what do we get here? 4 pi 1. 2 pi minus 0 is 2 pi. This is looking good. Oh, maybe it's not. And then pi minus pi is 2 pi again. Fuck. I don't think this works, does it? We just get pi. We just get pi. And we're supposed to get 1. Pi minus pi is 2 pi. Yeah. Fuck. Yeah, this doesn't work. We just get like... Do we get pi squared or something? No. Okay, so what we get here is 1 over... No, we literally just get pi. Oh, this is not good. We're gonna have to check something, huh? We're gonna have to check something. From pi to minus pi. Does that make sense? Or from pi over 2. Oh, that might make sense. That might make sense, actually. Okay, guys, here's what I'm thinking. The azimuthal, or no, the polar angle, the theta one here, it looks like this, right? We have boom, boom, boom. This one starts at the top and it sweeps all the way down here. But if you start at the top, this is not pi. This is actually pi over 2. Because if you start 0 here, this is pi over 2 and this is pi. So you start at pi over 2 and then you go boom here to negative pi over 2. Let me check if this is actually okay. So we have pi over 2, negative pi over 2. Pi over 2, negative pi over 2. And then here what we get is pi over 2 minus pi over 2. Is it the same thing? No, that one doesn't work either, does it? Because pi over 2 minus pi over 2 just gives us 2 pi over 2, which gives us pi, which is actually wrong. 2 pi. I feel like there's a 2 pi somewhere missing, huh? Alright guys, I actually checked the solutions, or not the solutions, but some extra stuff here. And what I'm missing is the Jacobian, which is an extra sine theta here, which is needed. So there's a sine theta here. And this azimuthal angle actually goes from 0 to pi. So not quite as simple of an integral as I was thinking. So this is something important that you guys got to keep in mind. Now we have to do integral of sine, which is minus cosine, I believe. And then we go 0 to pi here. So the first one was good, 2 pi minus 0. And then here we have minus cosine of pi minus cosine, so plus cosine of 0. Oops, cosine of 0. So cosine of 0 is 1, and cosine of 2 pi is also 1. Cosine of pi is just 0. No, it's not 0. Cosine of pi is it has to be minus 1, otherwise we're fucked. Hold up. Cosine of 0 is 1, and then it travels up. Cosine of pi over 2. Oh man, I peep a little unit circle. So here is 1 comma 0. Here is 0 comma 1, negative 1 comma 0, 0 comma negative 1. And here it's 0 radians, pi over 2, pi, and 2 pi, 3 pi over 2. This is a little unit circle. So cosine is the x component. Cosine of pi is minus 1. Minus 1 times minus is 1. Okay. Alright, I'm gonna actually keep this unit circle, so this one here is minus 1. And now this whole thing is going to be 4 pi times 2 pi times 2, which is equal to 1. QED. Thank goodness. Alright, so this is in one line what this looks like. Take a look at this, chillin'. Amazing. Now let's check the 0, 0. The orthonormality. I mean, what do we check orthonormality, or sorry, what do we check orthogonality with? We have to check orthogonality with the other one. And that's going to be hard. Is this true? 0, 2 pi, 0 pi. Square root of 1 over 4 pi. Then over here what we had was a negative 1/2, We had a square root of 15 over 2 pi, right? Then we had a sine theta, cosine theta, sine theta, d theta, and then d phi. Is that okay? Because we have minus 1 over 2, 15, 2 pi, oh, e phi here. Forgot an e phi. E to the I phi. So what did I do here? I'm just taking this one here and this one in the ket, because then I don't have to take a complex conjugate of this. It's not a big deal, but if you put this in the broad, then you gotta take a complex conjugate there, which is not a big deal. Multiply by this 0, 0 spherical harmonic, which we have here, and this one is minus 2 square root 15 over 2 pi, e to the I phi, sine theta, cosine theta. And here I have an extra sine theta d theta because of that Jacobian thing. When you take integrals in different coordinates, you have to add this little Jacobian thing. Just try to remember it. And okay. The challenging thing here is integration is going to be hard because we have a sine squared theta and cosine theta and d theta, right? And then we also have an e to the I phi d phi. So these are our integrals here with these bounds. All of this stuff over here is constants. We can pull those out. It doesn't really matter. So if we want to show this integral equals 0, we have to somehow just find a way to quickly show it equals 0, because either this integral equals 0 or this integral equals 0. We don't have to show both of them. Which one is going to equal 0 first? The problem is, though, I don't know exactly how to do this trig integral, but I'm thinking if we do u is equal to sine theta squared, then du is equal to 2 sine theta. Oh no, we can't do that. Huh? Oh no. Check this. U is equal to just sine theta. Then du is equal to negative cosine theta d theta. And we have this right over here. So this u sub simply becomes this with a minus sign. And that's actually pretty nice. But the problem is we have to use these things in here as well. However, sine of 0 is 0, and sine of pi is also 0. We get 0 minus 0 equals 0. Okay, guys, I found an easy way to do this integral. I found a very easy way to do this integral. Peep this. Alright, we're going to simplify this. So we have a constant out front. Then here we have a 2 pi, which goes with this, e to the I phi. And then here we have a 0 pi sine squared theta cosine theta d theta. Okay. We're going to do this second integral here because this one is going to give us 0. 0 times 0 times 0. 0 times anything is going to give us 0, and we're going to be QED chillin'. So peep this. Okay. U is equal to sine theta. So du is equal to negative. Derivative of sine is cosine, right? So we don't even have that negative. Cosine theta d theta. So now this integral becomes, the bounds here becomes 0 to 0. And how I'm doing this is I'm taking this 0, plugging into theta. Sine of 0 is 0. And then I'm taking this bound, sine of pi is also 0. So no matter what we put here, 0 and 0, this is an integral over a 0 bound. It's going to give you 0 regardless. But let's just write it out so we're chilling. We have a u squared du, which equals 0. So this whole thing equals 0, QED. Nice. That's pretty much all we did here. Very quick. Nice. Actually, I'm very happy with that. And if we do it the other way too, same thing is going to happen. So now the only thing we have left to prove is the fucking big one. All right. So we have this 1, 2, this 1, 2 equals 1. Is that true? This one's gonna fucking slam. 0 to 2 pi. 0 to pi. What do we have here? We had the first one, which is the complex conjugate, minus 1 over 2 square root 15 over 2 pi, I believe. E to the minus I phi. Here we have sine theta, cosine theta, and that's it. Is that true? Minus 1/2, 15 over 2 pi, e to the I phi, sine theta, cosine theta. Okay. And the next one is minus 1 over 2 square root 15 over 2 pi. Sine theta, cosine theta, close bracket, sine theta, this is the Jacobian thing. And then here we have a d phi first. No, sorry. Wait, I'm forgetting now. I think it is a d phi. Is it so? Did I read it wrong here? Here I was supposed to have a d phi. My bad. D phi goes with the 2 pi, doesn't? I think it does. Phi goes with the 2 pi. Yeah, phi goes with the 2 pi. Theta goes with the pi. Theta goes with the pi. And then d phi. So what I was just confused about is these bounds, do they apply to the theta or the phi? Phi goes with the 2 pi. Theta goes with the single pi. Nice. Now what can we simplify here? So we have a minus minus, 1/2 comes out. And then square root 15 over 2 pi comes out. Wait a second, I forgot an e phi here. E to the I phi. E to the I phi, e to the I phi. This equals 1, doesn't it? Okay. We can split the integral up. So the phi is the 2 pi here. And then here we have e to the minus I phi. E to the I phi d phi. Then here we have an integral. Sine theta, cosine theta, sine theta. Oh man, do we get to the same thing? No, we can't get to the same thing. Oh man, I'm scared. No, because they're being multiplied. They're being multiplied. Here we have a square, here we have a squared. D theta. Okay, so we have 1 over 2 square root 15 over 2 pi, 0 to 2 pi of just d phi. And what we saw before was this was just 2 pi. So 1 over 2 square root 15, 2 pi. And then here there is a 2 pi. Then here we had a 0 pi. How do we do this one? Sine cubed theta, cosine squared theta, d theta. It's not bad. We're actually moving there. We're almost there. We're almost there. But how do we do this integral? If we do u sub again, I don't know if it'll work. Okay, let's imagine we do u is equal to sine theta cubed, and then du is equal to 3 sine squared. No, it's still not going to work, is it? Times the derivative of what's inside. What's the derivative of sine squared? Can we just keep doing chain rule? You know what, guys? I'm gonna Google this integral. Wow. Here's how they do this integral. 0 pi. They keep cosine squared here, and they have 1 minus cosine squared. Replaces the sine squared, and you have an extra sine theta here, d theta. So they split this up into this form, like how we had it before. This sine theta stays on the outside. This cosine keep on the outside. This guy, sine squared x plus cosine squared x equals 1. Move this on the other side and you get sine squared x. Replace this sine squared x into that. Then you distribute this over here and over here. Then what do we have? Then, then we have 1 over 2, 15, 2 pi, 2 pi, 0 pi. So here we have cosine squared theta, sine theta, minus cosine to the 4th theta, sine theta, d theta, 2 integrals. And the answers to these look simple, but I guess it's because u is equal to cosine. Alright, I guess that makes sense. Here we do a u sub. U is equal to cosine theta. Du is equal to minus sine theta. U equals 0. Or hold up. We change the bounds. Theta equals 0 goes to u equals something, and theta equals pi goes to u equals something. So if we plug theta equals 0 into cosine, we get u is equal to 1, and then pi, let me check my little unit circle, pi is equal to minus 1. Minus 1 here, so this equals 1 over 2 square root 15 over 2 pi. 2 pi. Here what we have is this, and the top u is minus 1 now, the bottom u is 1. I don't like these bounds, but that is okay. Here we have u squared. Minus u squared du, and then minus minus 1, 1. And then here we have u to the 4th minus du. Alright, so what we have now, 1 over 2 square root 15 over 2 pi. Here we have a 2 pi. Here we can flip the bounds and remove this minus sign, so we have that u squared du. Here we can add those minus signs and minus, and then split this like that, u to the 4th du. So now we have 1 over 2. Does this work though? I don't know if it works because this pi doesn't get cancelled with the square root of pi. there's a pi here that's blessing us. But what we have here now is u squared, which is, let's see, we have u like that over 3, 1 minus 1, minus u to the 5 over 5, 1 minus 1. We have 2 square root of 15, 2 pi. I'm honestly worried about these prefactors. But it's okay. This whole thing gets multiplied like this. So we have 1 over 3 plus, plus minus 1, 3 minus 1 over 5 plus 1 over 5. Okay. Now let's start working here. Oh man, this is not looking good. This is not looking good. This is looking like ass. Alright, 1 over 3 plus 1 over 3 is equal to 2 over 3 minus 2 over 5. Come on guys, give me something. Give me something, please. So if here we have 15, 10, and then here we have 3 times 5, 15, 3 times 2, 6. Two pi. Here we have 10 minus 6, 4 over 15. Okay. This guy cancels with this guy. This becomes a 2. That becomes a 4. What we have now is square root of 15 over 2 pi. 2 pi, and then we have a 2 on 15. This is still looking bad. Still looking quite bad. But maybe we got this. Okay, let's bring everything into the square root. It's not gonna work. Bring everything into the square root. So 15, 2 times 2, 4, brought into the square root is 2, pi, brought into the square root is pi squared. Then here we have a 2 pi, which was from the beginning, and 15 squared. No, something is wrong here. Because here we have a 2 and a 2 cancels. One of these pi's cancels with one of these pi's. One of these 15s cancels with one of these 15s. I know what I did. I know what I did. Check it out, guys. Or do I know what I did? Check it out, guys. In the beginning, when I started this integral, I pulled out these factors, but I just pulled them out as is, and I only multiplied this thing. I should have multiplied this 2 together to give me a 4, and I should have multiplied these guys to get rid of the square root. So then the square root gets canceled all the way down. There should have been a 4 here. If there was a 4 here, that 4 cancels with this 4. Then this doesn't have a square root. This cancels with this. This 15 cancels with this. Okay. We get a 1. Alright, thank you guys for watching. I know this is quite crazy, but let's do a quick summary. Once the functions are created, make sure to create this. And what is this? You have to create the integral. And the integral is super important. First of all, you have to know the bounds of the variable you're talking about. And second of all, you have to know the Jacobian. Then throw in the function in here, simplify. Make sure you get 1 if the function is the same. This is normalization. If the functions are different, you have to get 0. How do you get 0? You can just look at one of the integrals. In my case, I looked at the d theta integral, which went from 0 to pi, and I looked at this here. How did I do this integral? I did a u sub. I said u is equal to sine. The derivative of that is cosine. Then this cosine here and d theta is just replaced by the du right here. U becomes u squared because it's sine squared. But then we also have to change the bound, so I plug 0 into this to get the bound for u. Sine of 0 is 0, and sine of pi is 0. So this integral just gives me 0. This is the easy way to do this one. So this is an important thing. Please remember this. Then for this one, we have this integral here. Just remember, multiply these factors out front, and then the same thing follows through. Crazy video. As always, you know, these videos are mad. 1 hour 9 minutes. Thank you guys for watching. Actually, if you're interested in where the spherical harmonics came from, check the video before that where we talked about the differential equations. If you want to see a solution to that differential equation and a derivation of the spherical harmonics, let me know, and I will see you guys in the next video. Peace.